Okay, so we're going to talk about numbers. Specifically, we want to get to complex numbers and rational numbers, basically um, finding things whose squares is something, cubes or something, etc. Before we get there, I wanted to um, remind you where all these other numbers came from, because I think that's useful insight. So that's what this will be about. All right, so let's start at the beginning. So what's the first kind of numbers? It's counting numbers, right? 1, 2, 3, 4, 5. It was very useful to count things. And so that's what we did. We came up with words to describe different quantities and symbols and all that. And then we also developed rules for, because um, coming up with names for every number distinctly is hard. So we came up with rules for, basically reusing names. So like 22 is 2 tens and a 2, right? So 1, 2, that's a 10, another 1, so that's 20, and then 2, right? So we didn't come up with a new name for 22. We reused the old stuff, right? So that's, and it gets, as the numbers get bigger and bigger, you see that kind of redundancy happening more and more. Good. So that's counting. And you can still ask, what is a number? And so that leads one into the idea of sort of canonical representations of these numbers. It's really hard to just say what 3 is, but it's pretty easy to show what 3 is, right? So this is what 3 is supposed to be. I got 3 fingers being held up, and that represents 3. So the idea is any collection of things that map to these like 3 fingers. So like I know that this is also 3 because these go like that, right? I can match them up. If I had 4 fingers, well, I'm missing a finger. Or if I had 2 fingers, I'm missing a finger to map to on this hand. So there's that notion. And then there's the notion of a canonical representation of these things. And here's where a little bit of cleverness from mathematicians come from. Had this idea of a set or container, and basically 0 is empty. So it's just the empty container. So I got nothing in there. That seems like a reasonable thing to accept the existence of. But it is something you have to accept the existence of. I mean, if you can't accept the existence of nothing, what do you have? You've got nothing. Wait. Okay. Anyway, the next one was 1. And that was supposed to be the set containing 0. So now we take the one thing we got, which was the thing containing nothing, and we put that in to another container, and that's 1. And it represents 1 because it's got one thing inside of it. And then we had 2, which is just 0 and 1. So you put 2 things in there. You've only got 2 things at this point, so you put them in. And then 3 is the same with that, but now it's 1, 2, 0, 1, 2. And you just keep on going. So that keep on going is a whole big story. You have to say what that means, but basically all the numbers that came before you put in the next container, and that's how you build up your numbers. Then one assumes that this just goes on forever and you create an infinite set of numbers. We don't really care that much about that at this point, but it's a thing. It is an assumption. And it's an assumption because you can imagine a world in which that doesn't happen, right? That there's the math world, which doesn't exist in the same sense of our reality, but you can also say, in this reality, do we actually have something that's infinite? We don't know that. So, if we wanted the numbers to all be represented by an actual collection of things of some kind, if we demanded that, then we probably wouldn't have an infinite set of numbers. But in mathematics, we just go, it's fine. We'll just assume it exists because it's useful. And that's fine, we know what it means. No problem. Now, we defined addition was, so fundamentally addition is like I've got 4 things and 2 things, and I put them together and I count them. So that's 6. And so the same thing is with this idea. 2 plus 3 is you have one color being red. So that represents 2. And then you have green being 3. And you put them together and you count. And so then that's like 5 things. So that's equal to, so that's equal to 5. And that's addition. All right. And you have to think about, to what extent that makes sense. If you do other combinations, does it, so like if you did 3 plus 2 instead of 2 plus 3, is that the same? Yes. If you did 1 plus 1 plus 3, is that the same as 2 plus 3? Yes. But you think through all these things. And so then there's multiplication. So this, I don't really even need other colors. This is we pair each thing in each of the containers together. So 0, 1, 0, 2, oh, sorry, 0, 0, 0, 1, 0, 2, and then 1, 0, 1, 1, and 1, 2, right? 6 things. That's equal to 6. So I just paired all the elements in there together, boom, boom, and counted. So that's multiplication. And again, it's 2 times 3 the same as 3 times 2? Yes. If you had like 4 times 2, which is 8, is that the same as 2 times 2 times 2? Yes. And then there's the good old distributive property, which is like 2 times 3 plus 4. So that's supposed to be equal to 6 plus 8 equal to 14, right? So you distribute. Right? And the picture is basically, what is that picture? Yeah, so we've got 2. You can think of this as 0, 1, so those are my rows. And then you've got 0, 1, 2, 0, 1, 2, 3. Versus 0, 1, 2, 3, 4, 5, 6. So that's 7, and that's 3 plus 4, right? And so that's kind of a pictorial proof of the distributive property. It's just basically you can count one side of this large box and then the other, or count, everything in a row, everything in the next row, and so forth. All right, so that's the natural numbers. So that's the natural numbers. Includes 0. I say that specifically because in a lot of K-12 texts, they don't include 0. I don't know why. I guess because you start counting with 1 because you got something. You don't count with 0 because 0 is nothing. However, in math and computer science and so forth, actually starting with 0 is a pretty good thing, practically speaking. And then there's also just the fact that in our construction, 0 was a natural thing to start with because that was nothing. Right? Start with nothing. Okay, so that's natural numbers. Everything's cool. We know about addition, multiplication, subtraction and division. So subtraction undoes addition. And division undoes multiplication. Okay, so that's that. But, so we can do something like 3 minus 2 is equal to 1, but 2 minus 3 equal to minus 1. Not yet. Right? We don't have the notion of a negative number. Likewise, we can do 4 divided by 2 equals 2. That's fine. 4 divided by 3 equals not yet. Right? There's no natural number that you can get from dividing by 4 into 3. You could, of course, just take whatever's left over. So like the minus 1 you could set to 0. Say if you're subtracting more than you got, you get 0. If you're dividing, get rid of any sort of non-natural number bits that are left over. So 4 divided by 3 is just 1 in that sense. Makes life a little easier. And there's definitely a lot of uses for that kind of thinking. But maybe one wants to go further. There's also powers. So this is like 2 to the 3 means 2 times 2 times 2. It's 3 times. So addition is sort of like repeated counting. Multiplication is repeated addition. Raising something to a power is repeated multiplication. Raising something to a natural number power. Anyway, that's 8. So that's powers. And again, you can undo. Well, actually, the notation isn't there yet. I guess you could do that. So say that is the cube root of 8, and that's 2. So that's the cube root. So that just undoes powers. And again, most of the time that's not going to work out terribly well with natural numbers. The cube root of 10 is not a natural number. It's not even a fraction. So there you go. All right. So that was the natural numbers. Now let's talk a little bit about integers. These are the negative numbers. All right, so where are they coming from? Well, the simplest place to come from is simply wanting to kind of undo addition. And let's just say we want a number such that x plus 3 equals 0. So how do we cancel 3? Canceling 3. So this, of course, is what we want. And so how do we do that? Well, basically, we come up with a clever idea. So we don't have negative numbers. We want to get negative numbers. We want to be able to solve this thing. We want to be able to talk about minus 10. All right. A lot of times this doesn't ever get talked about. It's just like, oh, these are just the negative numbers, and you can just add them and whatever. But I want to give you a little bit of a actual thing. So the idea is integers as wealth. And so we have sort of our assets. You can think of that as just cash. And debt. And then the wealth is that total. And you can kind of think of it as assets minus debt. Right? Now it's in quotes because your debt might be more than your assets, so you have a negative number. So we're trying to find the negative numbers, but so the idea is this total, the assets and the debt, is your integers. Good. Now, so for example, 4 and 2 would be, I have a wealth of 2. And 2, 4 would be, I have an overall debt of -2. So the first one, I have an extra $2 than I owe. And the other one is I owe $2 more than I have in assets. And so what you can do is anything that gives you the same total wealth is equivalent. So like 5 and 3, that's also +2, right? And what did I do? I added 4 plus 1 and 2 plus 1, right? So basically AB is same as A plus C, B plus C, basically, right? And then you sort of get your canonical forms. This is where kind of the magic happens. Of A0 is plus A, and 0B is this minus B. So that's the concept. You add them sort of component-wise. So if you're like merging two people's wealths together, right? You add up all their assets, you add up all their debts. If you want to multiply them, it gets a little bit more complicated. You can figure it out. It's fine. I'm not going to get distracted by that right now. But you do it in such a way that as you multiply them, essentially, well, one, you need to make sure that it doesn't matter what representative you have. And so you can essentially find out what the answer should be by going to the canonical form and doing it, which would actually be fine. And then, but you also want the distributive rule to apply and all these other rules. And so you write it down in such a way that that works. And essentially, I believe this would be AC. So multiplying positives together, and if you multiply two negatives together, you also get a positive number. So you can add that. And then multiply positive and negative, you get that, right? And so, you know, if you think of multiplication as, I guess I should just write down also the addition, just for completeness. Yeah. So that's easy. You just add them component-wise. And then the multiplication is you essentially think of each of the components separately. And then, well, actually, here's how you do it. You can think of it as A minus B times C minus D, right? That's essentially what we're doing here. And so then you write down your little box for multiplication. You get AC, you get BD, and you get minus AD, and then minus BC. And then the second, so you're getting AC plus BD plus, or sorry, minus BC plus AD. All right, so that's where that's coming from. But the idea of, you know, why is a positive times a negative? Well, you can think of the positive one as saying, you know, we're going to do this thing, like, let's say you're doing 3 times minus 5. We're going to do 3, we're going to subtract 5 3 times. So minus 5 minus 5 minus 5, that's minus 15. It's negative. You can also think of minus 5 times 3, and that's sort of thinking of removing the sort of cash 5 times. So that's lowering the asset part by 3, which is the same as raising the debt 3 times, or 5 times, 3 each choice. So that's why the negative times the positive is negative, and then negative times negative, well, it's kind of like you're repeatedly removing a debt, which is the same as adding to your assets. So that's integers. Again, all the usual rules. You can, you know, if you add 3 plus 5, it's the same as 5 plus 3. 3 times 5 is the same as 5 times 3. Same thing with all the negatives. Distributive property works. All of that good stuff. And that should all be, like proven. But it's fine. It's true. Oh, and so these are the integers. And we have a little like script z. And now we're going to do the rational numbers. So what are the rational numbers trying to do? Rational numbers are trying to undo multiplication, right? So 3x equals 1. We want to be able to say that this is 1/3, right? So what does this mean? And so in general, we're trying to solve mx equals 1, or x equals 1 over m. And then, or I guess, well, all right, how about trying to solve bx equals a, x equals a over b. Okay. All right, so that's what we're trying to do. Just like before, most of the time we don't actually have this in our number system yet. 5 divided by 3 is 5/3. It's about 1.4. And that doesn't exist yet. That's not an integer. Good, fine. So what do? Well, we just define a over b as, again, this pairing ab. So now it could be, it can be rationals or whatever. But so we've just created yet another number in a very similar fashion. Only here, the key relationship is that of scaling. So r times, so basically, let me just do an example. 5/3 should be the same as 10/6, right? That's what we want to be true. So we define that equals RA, RB. All right. And don't be multiplying by 0 for this. Basically, this is like the reducing top and bottom. And, the picture is, so if I've got 5 things, sorry, 3, yeah. Well, I'm doing 5/3. So I break up a, So this is 3. Okay. And 5/3 represents this. Right? Now, if I do the same thing, but now I'm going to divide this stuff into 6. Oops. So that's 6. So I'm going to count this, and this is 10, right? So it's like, it is different. Instead of dividing this thing into, I don't know, groups of 3, I'm dividing them into groups of 6. But the total like area, so this is like, this represents, kind of represents sort of fractional area, you might say. So you've got something of some whole divided up into these smaller pieces. Count how many pieces of that big whole you had. So there's a unit kind of area. This is what I mean by 1. And then dividing that into 3. One of those subunits tells me what 1/3 is. And so it's very much tied into notion of units and area pictorially. And basically, if you divide everything up, like if you have everything you've got, then you're doubling the number of regions that you've just created, right? So it kind of goes lockstep. And you can combine them until you get to a point that you can't, right? So 10⁶, if you had 10⁶, you can think of that as 5/3. 2 times 5 divided by 2 times 3, cancel the 2's. Yeah. Right, so that's the idea. Okay. And now, with this, again, you have to set up, well, one, you've got to know that the thing you care about, that whatever you're doing with your numbers, you've gotten the correct sort of form, and that, how do you add them, how do you multiply them? So basically the idea of multiplying fractions, and you could check this with trying to divide things up with boxes or whatever, is you just multiply the top and bottom. So AB times CD is just A times C and B times D. All right. So multiplication's easy. Addition, however, is not. For that, basically you want a common denominator above them, and then you can count them. I'm not going to get into the why of that, but basically that's the form, and so we would write this, and so this is kind of a definition of the multiplication here. And you'd have to see that if you scaled either of these things, that this thing would get scaled too. So like replace like AB with 2 times AB. So that's 2A and 2B. You put that in for A and B, 2, 2, 2. So all of those terms got multiplied by 2. So is double that, right? So it fits. Anyway, so that's rational numbers. So just to kind of review, natural numbers, we create these things out of containers, empty container, and then container with the 0, and container with the 0, 1. That's to make canonical representations of sets with a certain number of things so that you can always do the mapping. Integers was this idea of wealth. And we just made this pairing, right? So one thing kind of takes care of the positive bit, and the other thing takes care of the negative bit, and you can just reduce these down until you can actually say whether it's negative or positive, right? Just and that was trying to solve the equation x plus a equals 0, right? We wanted to get negative numbers for that, and makes it nice. And then the rational numbers. Yeah. So, rational numbers are things like that. That makes sense, right? Kind of a boldface Q. That's rational numbers. I'm going to say the Q comes from quotient. Anyway, so that's the rational numbers solve the equation, ax equals b, x equals a over b. Good. I mean, I guess you could also say integers was x plus a equals b, so x equals b minus a. Anyway, so you can subtract anything because of the integers, and you get something in your system. And you can divide by anything, and you get something in your system. And now we get fractions. You can multiply by fractions, multiply by negative numbers. It's all good. So we're all happy and dandy, right? Good. Well, all right. Now we come to finally the complex and real numbers. And I'll do them in more detail separately, but just to give you the sense of what we're trying to do here. So now we want to solve x to the n equals a. All right, and so a couple of examples: x squared equals 4. Actually, sorry, let me do 9. And that's x equals 3, because 3 times 3 equals 9. All right. We also could have been x equals minus 3. Minus 3 times minus 3 equals 9. So 2 solutions. So that's new. The other stuff always had 1 solution. Now we've got 2 solutions. That's cool. X squared equals 10. Right? We don't know. There is no natural number that does that. There's no rational number that does that. We need a new number. Need a new number. But we could get close using rational numbers. We can get as close as we want to a number whose square is 10. So there's that going for us. And we just kind of write it as x equals the square root of 10. Need to make that up. So we need to first kind of get it into our system, and then we need to actually show how to compute it, right? So define it. And 2 is computed. All right, so that's one set of problems. And it can be, x cubed, x to the 5th, whatever. And basically what we end up doing is we get, x equals a to the 1 over n. So that's what we're introducing, this 1 over n power. Need to say what that is, how to compute it, etc. All right. So that was a positive Now what if, well, if a equals 0, then x equals 0. That's easy. 0 squared is 0. Nothing else times itself will ever be 0. Good to go. And so now you have a less than 0. This is positive, and this is negative. Right? So negative numbers. So x squared equals, just a random thing here, minus 1. Now, if you multiply any integer, any rational number, times itself, you will get a positive number. Minus times a minus is a plus. Negative times negative is equal to plus. Problem. Right? Also plus times plus. Plus times plus is plus. So there's no way to get a number for that. So we just create something new. Create new thing. I equals the square root of minus 1. So that's the unit imaginary number. And I squared equals minus 1 is the defining property. Notice that minus I squared is equal to minus 1 squared times I squared. Powers distribute cross multiplication like that. And so you get plus 1 here, and you get minus 1. So that's minus 1. So minus I is also a square root of minus 1, so we could have chosen either one. In some sense, we don't really know what we chose, right? It's just something new, and the negative of it also works. Whatever we chose, the negative would always work, right? So anyway, just go with I. And so with these complex numbers, we can write, so we have a complex number. Well, all right, so first of all, when we define these square roots and whatever else, we'll end up defining the real numbers. I'll have to say that language now. And this is basically all decimals. So 3.14159. Right, so that's like pi. The decimal expansion goes on forever. Including that in there that's a real number. It's actually an irrational number. If no pattern, then irrational. I should say repeating pattern, then irrational. Obviously, there is a pattern to computing out pi in the sense that we can compute it out. But it's not a repeating thing. It's not like, so, oops. So it's not like 5.3272727727, right? So that's a rational number. This is a rational number. It repeats forever. And we can compute that out. What kind of fraction that's related to. But if it doesn't repeat like that, then that's an irrational number. And we put all of them together as the real numbers. This is to contrast it with the complex numbers over here, where this is of the form, let's say, v plus wi, or maybe iw. So yeah, that's a complex number, and v and w are real. So it could be like 2 plus 4i, 3 minus 4.2i, we could do pi plus 2 pi I. Right, whatever. Need to define addition and multiplication and really show how all this stuff works. So other videos will cover the details of this, but broad strokes, we want to solve the equation x to a power equals something, and by doing so, we get the real numbers if we're trying to deal with x to the n equals a positive number, and we get the complex numbers dealing with x to the n equals a negative number. And as it turns out, once we've included all of these numbers, we can find solutions to a huge slew of problems. All the quadratics, polynomials, they all have solutions at this point because we've included it. So it's a very powerful system that we've constructed. The real numbers also give us rise to very interesting functions, which we'll hopefully get to talk about later. Exponentials and logarithms, trigonometric functions. There's a whole rich structure in there of amazing stuff. It's really kind of interesting and deep, and we'll pursue some of it soon and some of the other stuff later. All right, so we need to talk more about the real numbers and the complex numbers.